Seal-in circuits. A seal-in circuit is kind of like memory. It's a way of remembering that something has happened. In industry and industrial machines, the switches are typically not like the light switches you find in your house. In your house, when you flip the light switch, it stays in whatever position you left it. You have to go back and switch it again if you want it in the other state. But most start and stop buttons in industry are momentary instead of toggle types of switches, and so you have to push the switch, and then when you release it, it changes back to as it was before you pushed it. They're spring return type switches. And so the question becomes, all right, if I press a start button, say on a drill press, how does the drill press keep running without me just holding the start button down? Well, seal-in circuits are used for doing that. So there's usually on a motor contactor an extra switch for maintaining the circuit. So when you press the start button, as you see, we've got an L1 and an L2 on either side in this hardwired setup. And when we press the start button, current can flow from L1 through the start button, which is normally open, but we're pressing it so it's closed, through the stop button, which is normally closed, and then into the coil for the motor starter. So the motor turns on, right? But as soon as we release the start button, then current can no longer flow through the start button itself. Rather, it has to flow through a switch that coil, that M coil pulled in, that is now connected. It's a normally open switch, but remember we applied power to the coil that pulls on that switch, and so now that switch is closed, and power can go through the M seal-in contact rather than through the start button, and thereby maintain power to the relay or to the motor starter coil. Now this is a hardwired setup, and on smaller machines there may be a setup just like this. There's no real need for a PLC on several types of smaller tools and things. But if you have a larger machine, then often what you'll have is a program instead of the hardwiring. So the start and stop buttons, as well as well, you don't really need the seal-in contact anymore. You don't really need the extra switch, but basically you need the start and stop button, and then the seal-in can be an internal memory coil, basically. So how would that look if we programmed it? How would we hook it all up? Well, here's a simulated seal-in circuit that I've written in ladder logic for the Click Koyo line of PLCs. You can see on rung 1, in fact there's only one rung, except for the end rung, which is just a byproduct of that language. The start button, when it's pressed on input 1, we're assuming we have a normally closed stop button. Power can flow through the start button, which is pressed through the normally closed stop button, and then the output to the motor coil comes on, Y1 comes on, but Y1 can be referenced as a memory address back as a switch and a condition. So even when the start button is released, which comes into the input driving input X1, even when that's released and X1 is no longer transmitting power, this motor starter coil Y1 can transmit power and maintain Y1 on. Here's a more complete view of the setup in an actual controller. There's many different manufacturers of controllers. Allen Bradley makes a wide range of them, as well as Siemens and Omron, and obviously Automation Direct makes several or has their own sort of house brand. But we see power between L1 and L2, so there's electric potential there. We don't really care if it's, you know, AC current, DC, whatever is necessary for driving the PLC and everything. We're assuming that's what we have. And then notice that there's a fuse on L1. That's what that pink little box is. But beyond that, L1 and L2 come in and provide power to the PLC, so the PLC can actually run its program. You can see the program inside of the PLC with I2 and I1. Apparently I1 goes to the stop button, which is normally closed. I2 goes to the start button. That's just the way this happens to be wired up. And then Q1 is an internal coil. It's an output associated with terminal output 1, but it's also an internal memory address, so it can be referenced on the left as Q1 bypassing I2 or the start button. And so it's the classic seal-in setup, so that when the start button is pressed, current flows through Q1, maintaining Q1 even when the start button is not pressed anymore. And so the output Q1 turns on, or in other words, provides the other leg of power that is missing so that the motor starter coil can turn on. Notice that the motor starter coil is always connected to L2, but it only gets L1 when the PLC provides that connection between L1 and the motor starter. There's one more thing to think about, and that is the stop button. What stops these circuits? Well, remember, the stop button is a normally closed button. If we press the stop button, that will break the input I1. That means that instruction I1 will no longer be passing power. That means that the output Q1 turns off, and so now the switch Q1 associated with that output is off and the seal-in is broken. So you'll notice in all seal-in circuits you need some way to start it, but you also have to think about what you're going to do to stop or to break the seal-in.